Hello, welcome to Algorithms Simplified. Today we are going over number 975, odd even jump. This is a hard level Leetcode question, most notably used in a past online Google assessment. Today I will be doing a detailed walkthrough, explanation, and coding out the solution to this problem. I will be coding in the end with Python, but the logic should still follow with all other languages. First, let's go through what the question is asking in the first place. So let's call that what is 975 asking us to do? In the question, we are given an integer array called ARR. There are a few things we should know about ARR. Besides the fact that it is an integer array, it has the following restrictions. It is of size greater than or equal to greater than 0. In other words, there is at least one item in the array, and for each value in the array, each of them are greater than or equal to 0. So given this array, integer array of these restrictions, the question is asking us to code out something that can return the number of good indices in this array. So what does a good index mean in the context of this problem? All right, so here is where the notation gets a little tricky, but I'm going to try my best to explain as clearly and concisely as possible. The idea is that we have some arbitrary index I, an index I is a good index if and only if starting from I we can jump to the end of the array in the following way. If I were to jump to some index, let's call it J, the following has to hold. First, I has to be less than J. In other words, we can jump forward only. So we can't jump backwards in the array. We can't jump in the same spot, so we can't stay in the same spot. We can only jump forward. Secondly, there's a restriction on every odd jump and every even jump that starts from index I. So for every odd jump, odd number jump starting from I, so this means every first, third, fifth, seventh, so on and so forth, jump from the index I, J has to be such an index that array, so the value of the array at index I has to be smaller than or equal to the value of the integer at position or index j. And array j is the smallest such number to hold the above statement. So what this means is that array j, the value at this place I can jump to on an odd number jump, has to be the smallest such number that is greater than or equal to the value at position I. In a similar way, let's just copy this. The opposite is true, kind of like the reverse is true for every even jump starting from I. Let's copy this and paste it to save some time. So for every even number jump starting from I, that means that is its second, fourth, or sixth, and so on. So let me write that: second, fourth, sixth, etc. jump from index I. Index I has to be greater than or equal to the value at index j, and the value at index j has to be the largest such number. Such number to be smaller than or equal to I. Another very important thing to note, and I'm going to write this in a color that is very bright, is that if, so for number 2 and 3 restrictions, if there is a numerical tie, so in other words, if there is a candidate that I can jump to, and there are multiple such candidates that their values are equal, I jumps to the smallest index between the tie. So the smallest index between the tie. That is very important. There are some things, I guess some obvious things we can point out from these specs. So first, let's change the pen size. First thing we notice is that not every index has an odd jump or even jump. Because at any point in the array, you can't guarantee that starting from some arbitrary index, there's always going to be a value less than or equal to it afterwards. And you also can't guarantee that there's going to be a value larger than or equal to it afterwards. So it could totally be possible that we can't jump forward. The second thing, and this draws from this very important fact right here, is that because we have a certain way of knowing exactly which index to jump to if there were a tie, this means that we can only have at most one place for any index I to jump to on its odd jump and on its even jump. So let's write that out. There exists at most one. So it could, like before, we said it could very well not exist. One odd jump index and even jump index. So the next odd jump it can jump to and the next even jump it can jump to for any index I. Now, because this question may be a little difficult to understand from all these fancy words and restrictions, let's go over an example and see from a visualization standpoint what we're saying here. Okay, let's go through an example. This is the second example on the 3 examples that Leetcode provides. I'm not going to go through all the examples it provides because that would be a waste of time. So you can feel free to do that on your own. I feel like this example itself illustrates what we're trying to accomplish very well. So I'm just going to go over this one. So this is the sample array we are given. Let me write down its indices so that it's very clear. Again, the goal we're trying to do is that we're trying to calculate how many good indices are there. How many good indices are there? So let's follow the pattern we know and see how many there are. Okay, first, let's start at index 0. From index 0, our first jump is an odd jump, and we need to jump to the value after index 0 such that it is the smallest such value that is larger than it. So out of all the possible candidates after index 0, index 1 and index 4 hold values larger than or equal to 2. But because 3 is the smallest such value between 3 and 4, on our first jump or on our odd jump from 2, we jump to index 1. This is our odd jump. From number 3, we perform our second jump, so our even number jump. Now looking at all the indices after our current index where we are, that's index 1, we have to look for the largest such value that is smaller than or equal to 3. Well, the only possible candidates are 1 and 1. That is a numerical tie. And since there's a numerical tie, and we have this rule right here, we have to jump to the smallest such index between the ties. So we have to jump to index 2. From here, we need to do our third jump. Our third jump is an odd number jump. So we have to go to the smallest such value after our current index, so these two, that is larger than or equal to 1. And that would be 1, because 1 is smaller than 4. So on our odd third jump, we jump to index 3, And on our fourth jump, which is our even number jump, can we jump to index 4? Well, no, we cannot jump to index 4 because on even jumps, we have to go to a value afterwards that is smaller than or equal to. But since 4 is larger than 1, we cannot jump forward. So let's note that we cannot jump forward on our even jump from index 3 to index 4. So that means, unfortunately, index 0 is not a good index because we cannot reach the last index of the array. Okay, I'm going to move a little bit faster for the next example from index 1 because hopefully that explanation was very clear because I went pretty slow. All right, so from index 1, out of all the possible indices afterwards, our first jump, our odd number jump, has to go to the value that is the smallest, that is larger than or equal to 3. And the only possibility, well, let's give it some more space, is index 4, because 4 is the only value afterwards that is larger than or equal to. And since from index 1, we can reach the last index, this means index 1 is a good index. All right. Similar pattern follows for index 2. On an index 2, remember our finding before. There is only one, at most one place an odd jump index can jump to for any index I, and the same thing for even jump. Well, here, that still holds. Even though this is the first jump and not the third jump in a series, because it is also odd, and there is only one odd place, at most one odd place for any index to jump to, it will jump to the same place as before in our calculations. So it will jump to index 1. In a similar logic, index 3, number 1. And in a similar logic, we know that index 3 doesn't have any even places to jump to, so we know that index 2 is not a good index. Starting from index 3, there is only one option it can go to, and that is index 4, because it is the only value afterwards that is greater than or equal to. And since it can reach the end, it is a good index. Now, kind of arbitrarily, not arbitrarily, but kind of as default, since index 4 already starts at the end, it can already get to the end because it is existing at the end of the array. So automatically, it is also a good index. So in total, if we count how many there are, we have index 1, index 3, and index 4 that are good indices to start from, we return value 3. So now that we understand how this question works and what it's asking, let's see what sort of solution we can come up with. So the most obvious and most brute force way is to just repeat what we've done here in this example. So essentially, from any index, arbitrary index I, we are going to look forward. So let's write that down. So brute force, so from some index I, we are going to look forward until the end, so n-1, for its next place to jump to. We have to repeat this until we either reach the end, or there's no other place to jump to. Now, in the worst case scenario, in terms of big O notation, since we have to check for every single index after I, all the way till the end, that is an O of n search. And then we have to repeat this. In a worst case, we have to jump from every single index starting from I all the way till n minus 1. That is also an O of n operation. So in total, just to calculate if one index is good in a brute force method, this is already O of n squared. Now, if we repeat this, repeat for every index in our array, then it would be O of n times n squared, which is O of n cubed. This is terrible. This is something we do not want. So we have to figure out ways to optimize our solution so that we can make it more efficient. Okay, so let's start thinking about how we can optimize our brute force solution. Let's start here. The most inefficient process is searching up the next index it can jump to. Why is it so highly inefficient? Because as we noted before, there is only one place that an odd jump or an even jump from any index can jump to. It is inefficient because we are repeating the same calculations over and over again. If we were able to track, so the idea is, let's write it here. So let's add a page. First, we need to improve our finding and retrieving of the next indices. This refers to both the odd and the even indices. So the idea is that if we're able to store our calculations, so if we've already calculated the next odd index for an index to jump to and the next even index for an index to jump to, we only need O of 1 to retrieve. Next time we use it. This process of storing is called memoization. Not to be confused with memorization. Memoization, the storing of data or calculations that you've already performed so that you can use them next time. Okay, well, the problem is, can our strategy of storing the calculations beat O of n squared? Well, there is actually a very clever way to perform the calculations in a much more efficient manner. To show this smarter, more clever memoization strategy, let's first look at, as an example, how we would memoize the next odd indices of every single index in an array. So these are the steps that we will follow. First, we will sort every single index value pair in ascending order based on its value. And if two or more values are equal, we sort based on ascending index. Then we initialize an array to keep track of which index or which odd index a certain index would jump to next. And we will also initialize a stack, a last in, first out data structure. We'll get more into why we do this as we go through the illustration. Here, I'm just going to paste in hello, paste. There we go. I'm just going to paste in what steps 1, 2, 3 would look like. So here we have the array we went through during our example, and labeled in green are its indices, and in white are its values. We order everything in ascending order based on the values, and for numerical ties, if the values are equal, we start with the lesser index. Also initialized a stack and the array accordingly. All right. So the idea here is that, say we were examining some index, right, or index value pair. We know that every single pair that comes before it, assuming that this pair's index comes after their indices, can jump to them, and not just can jump, is going to jump to them on the odd index, so long as they don't have a better option to jump to. That's a bit of a mouthful, but let's see what this looks like in action. So once we've set everything up, we're going to do the following. First, starting with the first item in our arrangement, we are going to put it in our stack. What are we going to put in our stack? We're going to put the index in our stack. So index 2. Following that, in the next iteration of our algorithm, we're going to look at the next pair, which is 3, 1. First, we compare 3, this index right here, to the top index in our stack. We see if 3 is bigger than 2. In other words, can index 2 jump to index 3? Well, since it is bigger, yes, it can jump to index 3, which means for index 2, we pop that off of the stack and we go to, accordingly, index 2, and we put in index 3 as the next index it will jump to in an odd jump. Why does this work? This works because we always know that each pair following whatever is in the stack would be larger than or equal to the value of everything else in the stack. If the items in the stack can jump to the following pair, then we know for sure this is the next up, because this is the smallest of everything that is larger than it. All right, let's continue and see what to do. So accordingly, we also have to consider where the 3, 1 pair would jump to. So we also need to put index 3 in our stack. All right, now let's look at index 0. We compare it to the 3 right here at the top of our stack. Since our 0 is not bigger than our 3, meaning from index 3, we can't jump backwards to 0. This means that the 0, 2 pair is definitely not something the 3, 1 pair can jump to. And we add it to our stack. here's what's really interesting, and this is why we use a stack instead of just a queue or any other set or other data structure that can store information. As you can see, all the indices go down in ascending order. Meaning, if the smallest index available in the stack can't jump to what we're comparing it to, then there's no point trying even a bigger index if we already know the smaller index is too big to jump to whatever index we're looking at. That's why using a stack is much more efficient than, say, a set or a list or other sort of data structures. All right, let's continue and see what I mean by that in the next example. Now we're at the 1-3 pair. At index 1, let's first compare to the top of our stack, and that's index 0. Is 1 bigger than 0? Yes, it is. That means that index 0 would jump to index 1. So let's write that down right here. And since we've already figured out where index 0 would jump to, we pop it off of our stack. Next, we check the next item in our stack. Is 1 larger than 3? Well, no, it's not. Meaning that the 3-1 pair, or the pair that has index 3, cannot jump to index 1. So we leave that in the stack for possibly another pair to pick up. And we add index 1 in here. Next up and last up, we look at the 4-4 pair. First, is 4 bigger than 1? 4 is bigger than 1, meaning index 1's smallest such value that it can jump to that is larger than or equal to it is at index 4. So we write that down and we pop it off. Then we look, is there anything else in the stack that needs something to jump to? Oh, there is. There's index 3. Is index 3 smaller than index 4? Well, it is. So we know that index 3 can jump to index 4. And since we've reached the end of all the pairs, we just fill in 0 as a default value. So let's write that down. 0 is our default value for no place to jump to. And this makes sense because 4, the largest value, can't possibly jump in an odd jump to something else in the array, no matter where it is, because it's the largest value. There's no other thing that can be bigger than it. Okay, so why do we use 0? 0 makes sense because we cannot jump in the same place and we also cannot jump backwards. So even if we're looking at index 0, it can't possibly jump to itself. So 0 is a great default value for any index that has no place to jump to. And if we compare this array, the next odd index array, that's 1, 4, 3, 4, 0, to how we did it in brute force, you can see that it matches. We would go to index 1 on an odd jump. We would go to index 4 on the odd jump. We would go to index 3 on the odd jump. We would go to index 4 on the odd jump, and index 4 can't go anywhere. In a similar fashion, which I'm not going to go over, but if you think about it in the opposite way, if we sort based on descending value with the pairs, and we also use a similar method as we did right here with the stack and checking if the index in the stack can indeed jump to the pair we're currently at, we can also come up with the next even index array. Going back to our analysis of runtime, let's see if what we've just described in the memoization steps are indeed lesser than O of n squared. So let's calculate the time. Let's do this in pink because that's something I haven't used. All right, so first step, sorting. Sorting itself will be an O of n log n time. This is the most efficient sorting method. This can be any sort of sorting method you prefer, merge sort, quick sort, whatever you want. O of n log n, that's the fastest. And then initializing and array and stack, those we can assume to be O of n and O of 1. Well, based on what language you use and based on what IDE you use, it gets a little finicky. But for now, since O of n is going to be lesser than O of n log n, we can ignore those in big O notation. And now, the process of going through all of this, for each pair, adding it to the stack, comparing it to other values, and changing the value in an index, those are all O of 1 constant time maneuvers. And if we do this n times, so since we have to do this for every single pair in our array, that is O of n. So instead of O of n squared, in order to calculate our next odd indices, we only need O of n log n plus O of n, which is O of n log n. And this is significantly better than O of n squared. And again, this is for just one of the calculations of either the next odd indices or next even indices. But even if we were to do this twice, in big O notation, it is still O of n log n. So now that we're able to solve one of the key inefficiencies of our algorithm, aka always needing to look for the next jump in an ineffective way, we can consider that inefficiency dealt with. However, there is still one more inefficiency that makes our algorithm slow. It is this part, the repeating part. For every single index, we keep repeating its jumps until we reach the end or we reach no place to jump to. Why is this inefficient, you ask? Well, let's see. So in some array, let's say we have A, B, C, D. Okay, and for some reason we know that A can jump, A's next odd jump is B, B's next even jump is C, C's next even jump is D, and so on. Okay, so if we already know that B holds this pattern, do we need to repeat the exact same series of calculations for the next jump if we already know that B can either reach the end successfully or not reach the end successfully? Well, no, we don't, because if we can figure out if B can jump to the end successfully in the opposite start jump than what its predecessor is jumping to, then we don't need its predecessor to keep repeating the same calculations. So this sort of programming based on some base case and going kind of backwards based on information we already know is called dynamic programming. So the second thing we need to do is we use dynamic programming to efficiently determine if an index can jump to the end. So let's see this in an example so that you know what I'm talking about. Here is the array we've been working with the entire time, labeled with its indices in green and its value in white as always. The next odd index and the next even index are arrays we have calculated from step 1. So again, these are from step 1, and we know it's O n log n for the time spent. In the dynamic programming case, we are going to initialize two arrays that hold whether an index can start in an odd jump and get to n-1, and if an index can start with an even jump and get to n-1. Here's how it would go. So in dynamic programming, we start with our base case. This is something we know is always true. This is where we start. In this case, our base case is the fact that we know that the last index can always reach the end. So here, as true, I'm going to use 1, as in the last index can reach itself no matter what. Let's make a note here. So 1 represents true, i.e. we can reach n-1, and 0 indicates false, so i.e. otherwise it cannot reach the end. So in conjunction with what we figured out previously, this is how we would calculate it. So we would work backwards. So we would work backwards this way, starting from our base case. What does this look like? Let's first start here. Can index 3 on an odd jump start jump to the last? So we check its next odd jump index, and that's 4. Then for odd, its next jump needs to start on an even. So we go to even start good, or the array holding whether an index can jump to the end on an even start, and we see that it's 1. 4 can indeed jump to itself. A little obvious, but yes, it's true. So we put 1 here because 3 can odd jump to the end through index 4. Moving over. For even start good, how do we calculate? very similar fashion. What index does it go to next in an even jump? It goes to index 0. As we've defined before, index 0 is the default value for there is no place it can jump to. So we know that even definitely cannot reach the end if it doesn't even have a place it can jump to. Moving forward, the similar patterns are repeated. Here, we will see in the corresponding value starting from the odd jump, it will jump to index 3. And in index 3, can an even start get it to the end? Well, no. So what this means is starting from index 2, if we start on an odd jump, we will be able to jump to 3, but we know that 3 cannot start in a series that starts with an even jump that reaches the end successfully. So we don't need to calculate any further. Here, we know that this is 0. I'm going to go a little bit faster for the next few because I'm going to assume that you already kind of caught on to the pattern. So here, even start good. We check its next even index is 3. Can 3's odd index start go to the end? Yes, it can. So we don't need to repeat those calculations. We know that even start can reach the end from index 2. Starting from here, can index 1 go to a even index next? Yes, there is such an even index. Oh, sorry, I meant odd index next because we're calculating odd. Yes, it can indeed go to index 4. Let's go to index 4's even start. Can it reach the end? Yes, it can. We don't need to repeat any calculations. This can indeed reach the end. Here, can index 1, starting from an even start series, reach the end? We go to index 2 on our next even jump, and starting from index 2, its odd series cannot reach the end. We don't need to repeat this calculation. We know that we can't reach the end starting with an even series jump. And here, for odd, next is 1. And for 1, the even starts cannot reach the end, so we know we can't reach the end here. And lastly, for this right here, the next even index is 2 from 0, and going to 2's odd start, it can't reach the end. It's a 0. So we know that we can't reach the end if we start with an even start jump in the array. Great. See how this is so much faster than what we had before. For each of these searches in the array, assuming that we already have calculated all this in O of nlogn time, it's only a constant lookup time for each one of the indices we need to observe. It's one lookup to its corresponding next even or next odd index, and then one O of 1 lookup if it's not a 0. And we repeat this for O of n times because there are n such values in the array, and we do this 2 times, but since it's big O notation, this means this dynamic programming process only costs O of n. This is so much better than what we've had before. Another thing to note is that, yes, while we do have a more efficient algorithm, so let's see what in total, so time-wise, if we count step 1, the memoization of the next indices, that is O of n log n. We need to add that to the time taken to use dynamic programming in conjunction with what we've discovered in step 1, which is O of n, and that results in an O of n log n time algorithm. So much better than O of n cubed. However, there is a little bit of a downside, which is that the space complexity, because we need to hold these 4 arrays of size n, is O of 4n, which is, well, in big O notation, O of n. So indeed, yes, there is some trade-off, but because O of n log n is so significantly faster than O of n cubed, this trade-off is quite worth it. Now, in the end, you might say, okay, great, we have all this information, but how can we calculate how many good jumps there are? Well, again, if you remember from our observations when we discussed the rules originally, the odd jump index, since it's the same no matter if it's 1, 3, 5, or 7th jump, we can simply just look at how many, or let's do this, how many odd jump starts odd jump start series can indeed reach the end, aka how many ones are there in this array right here. And if we sum it up, we see that we get 3. This summing up is only O of n, so again, very fast, and doesn't really kind of overshadow O of n log n in the total calculations. And if you look at what we have here in this array in comparison to the brute force, you can see that we get the exact same thing. Indices 1, 3, and 4 are the ones that have the good indices, and in our odd start good array, indices 1, 3, and 4 have values 1 for true accordingly.
Hi, I'm just going to take a brief moment to pause right here and thank you for watching this far along if you have. Now, if you enjoy the content that I create and you want to support this channel, please do consider subscribing, liking, and commenting. This helps my channel so much in ways you couldn't believe, so that I can create more of these Leetcode walkthroughs and coding tutorials for you. Okay, now without further ado, let's get into the coding tutorial.
Now that we have figured out and walked through the theory behind it, it should be pretty easy to code it up. First, let's just declare the length of the array as the size n for convenience. And the 3 steps that we've talked about in our discussion or walkthrough is the following. First, we find the next odd jump indices. These are indices that the next, that a certain index will jump to next on its odd jump. We do the same thing but for even jumps. After we found those 2, we're going to use the above jump indices arrays to dynamically program and solve for odd start good and even start good. So let's make a note of that. Use the above jump indices arrays to find if each index can odd start and even start jump to position n-1. Great, and at the end we will return the sum of odd start good. Or in other case, let's say that the sum of odd start good is equal to the number of good indices. Great. Let's start. So going back, we initiate a stack. We also initiate the array of size n defaulted to 0 to keep track or hold the values. We will go through the index value pairs. So for index value in, and then we will do a sorted array, enumerate, that gives us all the pairs of an array. And I want to sort it not based on the index, but I want it to sort based on the first position value. In this case, it would be the value. I don't want it to sort based on index. I want it to sort based on value. Great. While, ooh. Okay, so while our stack is not empty and the last item on the stack, so the last index in there, is smaller than our current index that we're looking at, so the smaller index can jump to our current index, we will change the stack's last index in our next odd jump array to go to the index we're currently examining. We'll keep doing this until it's not true anymore, and then we will append our index. Great. And in the same way, in a very similar way, we are going to find the next even jump. Also initiated to the same thing, but now we have to sort the other way around. We have to reverse it because now we have to go from largest to smallest values. And instead of next odd jump, we are looking at next even jump. Amazing. So after we figured out those two arrays, let's initiate the odd start good array. Whoa, that was not space, that was an enter, my bad. And the even start good array, which is gonna be initialized with the same structure. And as a base case for our dynamic programming, we know that the last index can always reach itself. So here actually we can write a note. So odd start good. So the last index, which is n-1, can always reach itself. So that's 1. So it's always a good index. And even start good, the last item, is always 1 as well. And here we can make a note that 1 is equal to can reach n-1 and 0 is otherwise. Great. Now let us do the dynamic programming part. So we will work backwards from our base case. Since we've already filled in the base case, we start at position n-2 all the way till the beginning. For each index I in range n-2, going backwards by 1 each time until we reach 0. The next, or i's next odd index is equal to next odd jump I. And if I next odd, so if it is 1 and even start good, not if it is 1, but if I next odd is 0, then this if case wouldn't go through. But if it is any number larger than 0, it will go through. So, and even start good, I next odd. So there is a series that can continue from its next odd index till the end, starting from an even start. Then we know that this index, I, is good with starting on an odd jump and can reach the end. Very similar logic for the even part. So I next even is equal to next even jump I. And if I next even is not 0, so it is a valid, we can indeed jump to an even place from our current index I, and next, and following that, we can do an odd start jump from our I next even. Then our even start good is going to be 1. Great. So now the sum of all the odd start good, since the first jump is odd, is equal to the total number of good indices. So we return the sum of odd start good. Let's submit the code. Oh, I need to sign in. 1 second.
12 seconds later.
Okay, we're back. I just signed in. So let us submit. And great, look, it is accepted.